Okay, so where were we? So look at this ideal in here and just look at all the leading terms, right? This generates an ideal of R, right? Just say there. Of course, this ideal could also be the entire ring, right? Because some of the polynomials could be monic. That's a possibility. Okay, so now what? This ideal L of leading coefficients is finite. Say by okay, so we'll go from there.
Which one of those come from some polynomial? One of those might be a good guess for clarity.
Right. In fact, what I'm gonna do is start our generating set with polys. Let's say F1 up to Fn. With leading coefficients. A1, AN respectively. And a minimal degree. So that phi is minimal. I haven't found degree yet, but I will. Let me. So in other words, F1 is the smallest degree polynomial that has leading coefficient A1, F2 is the smallest, A2 is small. Okay. Now, tell me how far we've gotten so far.
We have covered all the leading coefficients.
Okay. So what does that take care of for us? Let's say degree of F1 is less than or equal to degree of F2 less than or equal to. So let's say that I've arranged these polynomials where the degree is non-decreasing. I claim F1, F2, Fn generates everything in gamma of degree greater than or equal to n. I'm sorry about that. There we go. Greater than or equal to the degree of the PSU. Anybody explain why that's true? I'm not saying this exactly. This statement isn't correct. I'm not saying this exactly right. Let me state this a little bit better. Let me state it correctly. Let f of x then f of x is equal to p of x plus gamma x. well. Let's say B1 X, F1 X, plus Bn X, F1 X. So if I've got an arbitrary element in here, then I can write f of x as g of x plus a linear combination of these fi's and okay, so this is me stating it correctly. So if I have anything in f of x, no matter how big the degree is, basically I can subtract off a linear combination of these things and sort of reduce this f of x down to a smaller g of x of degree smaller than the largest of these, right? Why is this true? Well, if g of x is of degree less than fn of x, this is certainly true because I can just let the rest of this be 0, right? And I'm satisfied, right? What if g of x has degree bigger than or equal to fn of x? Well, degree of f of x is greater than or equal to degree of fn, then leading coefficient of x of f of x is a linear combination of leading coefficients of FIX, right? So if L, well, let's say if B is leading coefficient of F, then B equals R1A1 plus RNA. Correct? So how does this translate? So note f of x minus R1 F1 minus R2 F2 minus Rn Fn. What can you say about this polynomial? Right, so the degree of f of x is at least this big. This is a linear combination, so the degree of this here is no more than the degree of fn. And notice that the leading terms, do they match? Maybe not. What could be the problem?
We have to, for example, multiply f1 for x to the degree of f minus the degree of f1.
Everybody agree with that? If it weren't for these pesky polynomials, then the leading coefficients would match. But we might have to multiply this by I1 x I2 up to like that. Do I agree with that? Now the degrees match, right? And what happens? What's true about this polynomial?
Now it's degree less than that.
Right. And the leading coefficients cancel, so the degree drops, right? And that's basically the inductive argument, right? So what do we have? We have f of x can be written as a linear combination of f1 up to fn, but you've got this remainder here, right? But what do I know about this remainder? G of x is left over. It has to be less than the degree of fn. Okay. Well, we still haven't finitely generated because we've got the g of x left over, right? Somebody save me. What else can we do here?
By minimality of the choices of FI.
Well, right, so here's what we have is we have all these possible remainders, right? We have remainder and our degrees are, so our degree of g of x is less than fn, so look at all polynomials that have leading coefficients that generate the g, all possible ones at degree fn minus one. Look at all polynomials in there that generate all possible g's fn minus two and so forth and so on, right? So at this point, I will sloppily say, throw in all polynomials needed to generate, and polynomials, of course, from gamma, needed to generate leading coefficients of possible means. Less than fn. So just cascade down from degree of fn minus one, throw in all possible g's with the, or all possible elements from gamma that will generate the leading coefficients of elements of gamma of that degree. Then you've got one less degree, throw in all the polynomials that you need that will generate the leading coefficients at that degree. Next degree down, throw in all polynomials from gamma that generate the leading coefficients at that degree. These are all finitely generated ideals, so you only need finitely many things. We've thrown in a lot of stuff, but we've only thrown in finitely many. Right, so we exhaust that out and we generate that. Everybody see kind of the outline of that? Now, here's a question for you. This is an interesting result by Gilmer. Theorem. Gilmer, around 68-ish, I think. If Rx is the theorem, then R is the theorem. With this is an interesting converse because what it means is if you have any polynomial ring that's Noetherian, it must contain an identity.
But
Yeah.
are we assuming R is just a commutative ring?
Yes, yeah. Then all must have identity. So in other words, if R is not, it's not, then Rx never is Noetherian. I find it rather fascinating. So before we explore this, let me ask you a question. This might anger the blood. If I did that proof right, and I certainly, I will be the first to admit that I wasn't complete, but the idea, even though I didn't put in all the extra details, is true, right? What do? The leading coefficients of everything in the ideal is finitely generated, so you have your first string of polynomials, or F, that this essentially takes care of everything of high degree. So now you've got it to where you've got a remainder that's smaller than the largest degree. And then what do? You just be a lazy slob, and the next degree down, throw in all possible polynomials that generate the leading coefficients at that level, and just go down. You throw in finite and you think you're done with this works. If Gilmer's right, which he tends to be, it's necessary for me to use the identity to get this result. Where I use it? I had to have used the fact that R has an identity somewhere. Where is it? What's that?
And these are,
Where?
I don't know, just asking, in these are, where? You want to generate all the, I don't know.
You have a hypothesis, Jared?
Where you do the Euclidean algorithm type thing here? Like, what if that is the same leading term as up then?
Actually, the place that is the most obvious to me is right here. If there's no identity, there is no X. I feel like, there is no spoon. There is no X. Right, so perhaps an example might demonstrate this. And Eric, before you jump on me, let me say, how about RX is a non-zero? How about that? Right, so we should probably look out for that, but yeah, I'm assuming R is non-zero. So let me take kind of a simple example here. Consider, this is about the simplest example of a ring without identity. Okay. You don't have to be a genius to figure out the addition multiplication of this one, right? Everything's mod 4. 0 plus 0 is 0, 2 plus 2 is 0, right? So this is basically the maximal ideal in Z4. And 0 times 0, 0 times 2, and 2 times 2 are all 0, right? This barely has a non-zero element, right? Because 2 is there being a non-zero element, but if you multiply it by itself or add it to itself, it's 0. However, let's call this ring R. Rx can you name an element of this ring? It's not finitely generated, or can anybody give me an ideal in this ring that's not finitely generated? Look at this thing, it's only got 2.
Generated by 2x, 2x squared, 2x squared.
That ideal is not finitely generated. That's enough to kind of anger up the blood a little bit, isn't it? But in this ring, there is no X, right? Because everything is a linear combination of elements in R times powers of X. There is no 1, so there is no X. And notice this ideal here, you're tempted to say, oh, look, this is in the ideal generated by 2, but no, it's not, right? Because you can't multiply this by anything in Rx and get 2x, right? And your problem just compounds as you go up, right? So this is actually a fascinating converse that, well, sort of converse that Gilmer had here. And the use of 1 is subtle. Yes.
this proof, that Gilmer, do, it's kind of like constructed, so if you have an idea, a ring without identity, you can for sure, easily found the non-finally generated idea, or does something change? That also not.
Are you asking about Gilmer's original proof?
Yeah, yeah.
I don't know.
Okay.
I don't remember. I don't even know if I've ever read his proof. I probably read that and I'm like, okay,
Okay.
this sounds like something to do while I watch TV, right? So, but anyway, yeah, I mean, once you see it, it's not very difficult, is it? But it's an incredibly, so that's what happens in math a lot, I think, right? There are things that are beautiful because they're hard to prove, right? And there's some things that are really beautiful that are just not necessarily hard to prove, but the observation itself is sort of important. Okay. Yes,
So my guess was kind of dumb because we just did it right here. Without the generalized like kind of Euclidean algorithm thing. We were able to do that though because of this B is equal to this linear combination, right? Like in general, to do that with the commutative ring, you need the leading coefficient to be a unit, right? Something like that. What we did here that you erased, like that Euclidean algorithm type thing.
no, you don't need the leading coefficient to be, as long as, here's what we knew that the leading coefficient, since f of x was an element of gamma, its leading coefficient had to be a linear combination.
Right, that's what I was saying. I was saying in this instance, we were able to do it because of this, but if you were just looking at a general ring, you can't, you need.
You need some condition, right? I mean, like, if you have if, for example, the leading coefficients were the ideal of the entire thing, that would be something to work with. But yeah, in general, it's difficult to know if you can generate something sometimes.
So I guess here, since multiplication is trivial, this would work for any infinite set. Or am I wrong? Any infinite set in Rx would be a non-finitely generated.
Oh, yeah, there's gonna be a lot of them. You're probably right. I'd have to think about it, but yeah, because I think to have an infinite set in there, you can't do that with bounded degrees, so you're gonna have to get bigger and bigger. So I think you're probably right about that. Okay, so here it is. A theorem. This one's easier to prove. Theorem, 223. Let R be a domain. In Rx, respectively, or power X, the ideal generated by X prime. So if R is an integral domain, and that's important, it has to be a domain, then in the polynomial ring, or the power series ring, X is prime, proof, consider phi from Rx into R, respectively, pitchfork from R power X into R, given by phi of f of x equals x of 0, and the same for the pitchfork. See, that's one thing for sure I can plug into a power series ring. Notice that well, as R is a domain, kernel of phi is prime. So the ideal generated by X here is prime in both situations. So I'm gonna write this down here. So that, I'm careful about it because, yeah, you know, I'm gonna try to carry this all together here. Yeah, so I'm gonna find, degree and order here. Definition, 224. So I'm gonna take two things on here. Oh, there it is. The computer version one. Comma, A0 plus A1X plus ANXN and RX. And, and here AN is not 0. And let's say BM XM plus BM plus 1 XM plus 1 in R power X. And here I want BM also to be not 0. So in this definition, you see that I'm talking about non-zero polynomials and I'm talking about non-zero power series. Right. One, we say, and let me call this F and G. We say that the degree of f of x is equal to n. So it's just the highest, the power of the highest non-zero term, the polynomial. And we say the ord of g of x equal to n. This is called the degree, this is called order. And it's sort of a dual notion, right? I mean, you're measuring sort of how big the polynomial is, what's the highest degree term. You can't do this for the power series, but what you can do is you can measure sort of the smallest coefficient that's not 0. But of course, again, these are assuming, of course, that f of x and g of x are non-zero. We're making that assumption here. Sometimes we say the degree of the zero polynomial is negative infinity. And sometimes we say the order of, sometimes we say the order of the zero polynomial is infinity, right? But well, I'm gonna beat that horse to death. Okay. So proposition. Let's let R be a domain. No, I'm not going to do that. Let R be community ring 1. Let's let f of x and g of x be in Rx. Let a of x and b of x be in R power x. Number 1. What can you say about this? What's that? This is less than or equal to maximum degree, yeah. Right. And notice if the degrees of f and g are different, it equals the max, right? And in fact, it may equal the max, even if the degree of f and g are the same. What might go wrong is the leading coefficients may cancel out, right? And two, what about this one?
It's all equal on this one.
What's an important case where you get an equality?
Really was okay.
Right, so degree n times degree m, you expect that to be a degree n plus m. Of course, if you've got zero divisors, that could go wrong. Three, how about the OR?
Don't equal on the minimum.
Right. And how about the product? Or AX times BX.
They don't equal on this one.
And again, equal if R is domain. I will probably leave this as an exercise for y'all to cogitate. We'll talk more about that next time. Any questions? All right, well, we will see you all on Wednesday.